In this video, we're going to begin to talk about section 3.4, which is called a library of functions. There are many functions in this section, but the only ones that we're going to focus on today are called piecewise functions. So, what is a piecewise function? Well, sometimes there are functions that are defined using different equations based on different parts of the domain of this function. So, as an example, we could take the absolute value function. Okay, so here's my example that f of x is equal to the absolute value of x. Okay, and if you look down below, we have the function or the graph of this function. Okay? And as you'll see, if we go left to right for the first half of this equation, it seems like the line, if we had to put an equation on this line, it looks linear, okay, and specifically it looks like maybe the function f of x is equal to negative x. Okay, so that would be a negative function, but it abruptly turns right at x equals 0, and then as we go from 0 to positive x, it now looks like the function f of x is equal to x. And that is, in fact, what's happening, and we relate, or we look at this function when we describe it algebraically, i.e. with an equation using this notation right here. Okay, then this is the piecewise notation that we're going to have to get used to, right, or that you will get used to over the next few slides. So it starts with a squiggly brace, okay, first, and then it has different rows, so to speak, and there's nothing but white space separating them, but there is a separator, and it says, or it gives you the value of the function, or not necessarily the value, but the maybe equation that you should use, or the part of the function for a given part of the domain. Okay, and so this is a piecewise representation of the absolute value function, and so this says when x is greater than or equal to 0, this part, then it looks like x. Okay? But when x is less than 0, the domain less than 0, then x looks like negative x. Okay? And so what we're interested in this section is analyzing different aspects of piecewise functions. So let's see what kind of things that we're interested in here. So for the following piecewise function, which you'll find over here, I want to find some values of the function. Okay, find the domain and the range, or the domain. Then I want to find the x and y intercepts. Then I want to graph the function. Okay, and then I want to find the range of the function, and I can use that, or I can do that by using the graph of the function. So first, let's find some values of the function. And so usually this is not a hard or tough exercise, but we need to be careful about the x values that we substitute in, and to which formula do we substitute them into. So let's first start with f of negative 2. Okay, so that means this is f of x, and so I'm substituting in the value of negative 2 to this function. The question becomes, which row 1, 2, or 3 do I use? Okay, and to do that, we need to read the domain of the function. Okay, and so we see where negative 2 lies. So is it greater than 1? Is it the third row? No, it's not greater than 1. Is it equal to 1? Also no. Is it between negative 3 and 1? And the answer is yes. So to evaluate this function, we're actually going to substitute negative 2 into that x value, into the sort of equation negative 2x plus 1. Okay, so you substitute in negative 2 for the x, and what you get is negative 2 times negative 2 is 4, plus 1 is 5. So f of negative 2 is 5. We can do the same thing, f of 1, so we need to find out where 1 is, and lo and behold, step 2 there, right here, says when x is 1, the function value is 2. Okay, so f of 1 is 2. That was pretty easy. And lastly, what about f of 2? F of 2, well, where does 2 lie in the domain? Is it between 1 and negative 3? No. Is it 1? No. Is it greater than 1? Yes. So it's greater than 1, so I'm going to substitute 2 into the equation x squared. Okay, and so 2 squared is 4, and so f of 2 is 4. Okay, so that was the values part. Not too bad, but we do need to keep in mind where the value that we're substituting into the equation, into the function, lies in terms of the domain. So next, speaking of the domain, we need to, I'll call this step 1, step 2, step 3, step 4, and step 5. Okay? Step 2 is to determine the domain of the function. Okay? And so the domain is what values of x can we substitute into this function to get something out of it. Okay? And so for this, we can look towards these 3 if statements over here. Okay, so it says that if x is between negative 3 and 1, less than 1, or greater than or equal to 3, then it's something. 1, it's something else, and then greater than 1, it's something. Okay, so the domain of the function is from negative 3, okay, so that's the lowest that it can go, so there's nothing defined there for anything less than negative 3. But how far up can we go? Well, this final thing here, greater than 1, says just greater than 1. So it keeps on going until it hits, or rather, till it ends at infinity. So the domain is from negative 3 to infinity. Okay? Next, we can find the x and y intercepts. And so we'll start first with the y-intercept because it's the easiest. Y-intercept is when f is 0. Okay, when x is 0, so I substitute 0 in, I see that that is contained in the first question, or the first part of the piecewise function. Okay, and so then I'm looking at negative 2 times 0 plus 1. And so f of 0 is 1, hence my y-intercept is at 0, 1. Okay. Then we'll look for the x-intercepts, which we remember from section 4.3 is we set the equation f of x equal to 0 and then solve. Now, this is the important part, or this is the challenging part about a piecewise function. Okay? We need to set each part of this equation equal to 0, okay, and see what we get out. So let's do that first for negative 2x plus 1. When we set that equal to 0 and then solve for x, we subtract 1, we get negative 2x equals negative 1, and then when we divide by negative 2, we get that x is equal to 1/2. Okay? So there is one possible x-intercept, and we do the same thing with the second one. We set 2 equal to 0, and you should ask yourself, can that ever happen? Can 2 ever be equal to 0? And the answer is no. Okay. And then we look to the last one, and we set x squared equal to 0. Okay. And so what happens there is that you can take the square root of both sides, and that you get x is equal to plus or minus 0, which is just 0. Okay. And so we have two possible solutions. We have x equal to 1/2 here, and we also have x equal to 0. But again, we must be conscious of the domain in which this was defined. So specifically, on which x squared was defined. Because x squared up here was only defined for when x was greater than 1. And down here I'm saying, well, the x-intercepts happen when x is 0. But I used the function x squared, but x squared is only defined from 1 on, okay? Or rather, greater than 1. So the long story short is that x equals 0 is not an x-intercept of this function, okay? So the only x-intercept is x equals 1/2. And so that would be the point 1/2, 0. Okay? So I have one y-intercept, 0, 1, one x-intercept, 1/2, 0. And I can use this now to graph the function. So I'm going to erase a little bit here, especially at the top, so that I give myself some room to graph. But we'll remember the stuff that I wrote down because it's going to help us in how we graph. So here are my x and y axes. I'm going to draw some tick marks really quick. That'll give us an idea of, a rough idea of where we're supposed to be on the graph. Okay. And so we're going to start off at -3. Okay, we're going to start off, we know, so we'll use our points that we know from the x and y intercept. We know that the y-intercept is at 0, 1. So we know that's there. And we know, maybe that's a little bit large of a circle. We also know that the x-intercept happens at 1/2, 0, which is here. Okay, actually, let me zoom in on my x and y axes here. Okay. Now, again, we know that the y-intercept happens at 0, 1 here, and we know that the x-intercept happens at 1/2, 0. Okay. We also know that when x is equal to 1, y is equal to 2, so we know 1/2, 2 there. Okay. And then beyond that, we don't quite know what happened. So let's start. We know that the graph starts at -3. So it starts at -3, which is here. Okay. Sorry, bad line. -3. Okay. And so we can substitute -3 into this equation to see the value that we get, okay, as a starting point. And when we do substitute -3 in there, you'll get -2 times -3, which is +6 plus 1, 7. Okay, and so that point is slightly off of our function. It would be up here. somewhere. And now you can look at our equation or function value here, our functional form. That's a linear function, okay? And so we know that there's a line between that and my y-intercept, because my y-intercept is also in this part of the domain. And in fact, the 1/2 is also there. So the line goes through it as well. And so we can continue on all the way down until we almost hit 1, okay? Because it says this continues until we get to less than 1, okay? Then what happens when we hit less than 1 right there is it jumps all the way up to 2, okay? So then there's a point at 2, which is this, okay? And then when it's greater than 1, we get that the function value is x squared. Okay, so if we did very close to 1 squared, okay, or really just 1 squared, we get 1. And so it would start right here, okay? But in fact, this would be an open circle because it's not including 1. Okay? And it would look like x squared, which is a quadratic function that we've had a lot of practice with. So if you substitute 2 in here, you'd get 4 out. So if we go to 2, 4 here, and then we drew a parabola up, okay, that's what our function would look like, and it continues on forever and ever. So I put a arrow there, okay? And so this is, I know it's a rough drawing, but it is our function, okay? So that's the graph of our function. And the last thing that we need to do is determine the range of this function, okay? So it looks like the lowest that we get is right about here when it almost hits 1. When it almost hits 1. And it looks like it would be, if I substituted 1 into this equation here, I get -2 times 1 is -2, plus 1 is -1. Okay, so if that was included, we'd hit -1 there. And so that's the lowest point that we see on this axis. Okay. So now I'm on to step 5, which is the range. It looks like the lowest point is -1, but we don't quite reach that, so I'm going to put a parenthesis there. And then it looks like it increases to positive infinity, and so the right-hand side of the range is positive infinity. Okay, so I know that was a lot of work. It took us a long time, but it was extremely important that we do all of those steps to get an idea of what this piecewise function looks like. So now I want you to take that information and the skills that we learned here and apply it in a your term. Okay, so what I've done is I've made a second function that looks actually surprisingly familiar to the function that we just did right here. Okay, and I want you to answer the following questions. So basically do the same thing that I did with that last piecewise function, now just to this piecewise function.